So we finished learning about ANOVA, learning how to deal with the assumptions, knowing what to do if we meet the assumptions and what to do when we violate the assumptions. This also includes post hoc tests. I know it's a lot of information, and that's why I put together a flowchart. It kind of gives you an idea, or at least a guidance on what to do under various situations. So this is posted on Blackboard. Our idea is that we've decided to run an ANOVA, so first thing we want to do is check the normality within the groups. And my recommendation is to use QQ plots. So once we do that, then we're either normally distributed or not normally distributed. And it doesn't really matter what our answer is, because our next task is to check for equal variances. Now, our answer for the normality question determines what test we have. So if we're normally distributed, we use Brown-Forsyth test. If we are not normally distributed, we'll use Fligner-Killeen test. So I'll start with the yes. So we're normal and we check for variance. Well, if we do have equal variance, then we can proceed with the ANOVA and ask, are the means different? If the answer is yes, then we proceed with doing a Tukey's test to determine which means differ, or a Dunnett's. The distinction between these two comes down to the question, our biological question. Are we interested in identifying which means differ, or are we only interested in comparing our treatments to some sort of control? In other words, we don't care what the differences are between the treatments themselves. We're only interested in if those treatments differ from the controls. If we don't have equal variances, then we can use Welch's ANOVA to answer the question, are the means different? If our answer is yes, the means are different, then our post hoc test that we'll run will be pairwise Welch's t-tests, and then adjust our p-values when we're done. Now for both of these situations, whether we run ANOVA or Welch's ANOVA, if we get a p-value that's greater than 0.05, we would conclude that the means do not differ, and then we stop. We're done. On the other side of the flowchart is when we are non-normal. So if we are non-normal but exhibit equal variances, then our options to answer this question is to just go ahead and proceed with ANOVA, or to try a permutational ANOVA. If we're slightly non-normal, I would use regular ANOVA and then follow that with Tukey's, HSD, or Dunnett's if we get a significant difference between the means. If we are clearly non-normal and it's very obvious and it looks kind of severe, then I would use a permutational ANOVA, and if we get a significant p-value, then I would follow that up with a pairwise permutational ANOVA or t-test and have a p-value adjustment with that. If we are non-normal and unequal variances, then our only option will be to run a permutational ANOVA followed by permutational ANOVAs or t-tests with p-value adjustments. So that pairwise permutational ANOVA or t-test, it's your choice as to which you would use. I've used both. We should get the same p-values. Like the situation when we have normal data, if our answer to the question, are the means different, is no, then we stop. We're done. That's it. So I have this ANOVA flow diagram posted. You can feel free to print it and follow along as you work through your homework. I also posted a diagram to help you choose different tests. Now, I didn't actually specify what test to actually run. It kind of depends on some of the questions, but at least I started to break it down based on the number of variables and the type of variables that we're working with. So if we have one variable and that variable is discrete or continuous, so a measurement type of variable, then we can do a display. So the display of choice will be a histogram. We want to show distributions of these numeric data. The tests available to us would be a z-test, a t-test, a sign test, Shapiro-Wilks, QQ plots, which I know isn't a test, it's an assessment, and also bootstrap 95% confidence intervals. Now, it depends on what our question will be when picking our test. So if we're interested in testing the means, well, we're going to use z-test or t-test or bootstrap confidence intervals. If we're interested in comparing a median, it's a sign test. If we're interested in determining if the data are normally distributed, well, we're looking at Shapiro-Wilk and QQ plots. If we have two variables, then it comes down to, well, what are the types? If we have one categorical and one continuous variable, like what we just finished, we can use box plots to illustrate those data. We could also do a graph in Excel or R that plots the mean with standard errors. That's okay, but I just left box plots since those are pretty easy to do in R. Our choice of tests are all of these. So again, which one we choose depends on the question. If we're interested in comparing means, well, we're going to use t-test, Welch's t-test, ANOVA, or Welch's ANOVA. And just kind of comes down to what assumptions we have and how many groups. So if we only have two groups, we're going to use t-test or ANOVA. If we have three or more groups, then we are going to use one of the ANOVAs. We also have permutational ANOVAs and permutational t-tests. So based on our assumptions, if we violated them, we can run permutational ANOVA or permutational t-tests. If we're interested in comparing variances between our groups, then we can use Brown, Forsyth, and Fligner-Killeen. If we're interested in comparing medians, we could use a Kruskal-Wallis test. And if we're interested in identifying which means differ, then we're going to use Tukey, HSD, and Dunitz. Now, with the Tukey's, HSD, and Dunitz, we have to first run an ANOVA to demonstrate that, yes, a mean, there is a difference in mean, and then we can follow with these post hoc tests. There are a couple other things included on this figure. So when we have two continuous variables, we're going to use a scatter plot or a bivariate plot to illustrate our data. When we have these types of variables, we're really interested in correlation. So are these two measurement variables correlated or not? And the test that we're going to learn is a correlation test and also a permutational correlation test. This will be next on our list of topics to cover. And then once we finish up the two continuous variables, we will move to categorical variables. So we will start with a one categorical variable, and cover these goodness of fit tests. And then we'll talk about the possibility of having two categorical variables. This is time permitting. If we don't get there in this undergraduate class, then we do cover this in our graduate level course. So hopefully these two flow diagrams will help you study for the exam and will serve as a valuable reference as you do stats beyond this class.